Welcome to this lesson on Reactors in Aspen Plus. We will be modeling the various kinds of reactors in Aspen Plus. We'll differentiate between the types. We'll also determine the types suitable for a specific problem and simulate the reactions under both kinetic and the equilibrium conditions. We, we will see how reactions, the different forms of reactions and rate laws are specified in Aspen Plus as well. Well, reactions occur in vessels known as reactors. And here, reaction is a process that leads to the loss of a reacting species' chemical identity. And so the species becomes something new. It changes identity in various ways. It can just be an internal arrangement, or becomes a completely new compound. So the, there are various ways in Aspen Plus to model this process. And when you go to the model palette in the simulation environment, you can see the various reactor blocks or equipment. And each one of them has its own format for specification and the way it works, what it requires, what it's good at, and the specific result it's able to provide. Right? So there are two forms of reactors broadly in Aspen Plus, and those are kinetic reactors and non-kinetic reactors, or reactors that do not require the kinetics of the reaction. And they usually require the reaction stoichiometry or some minimal specification. And most of them are essentially mass balance, energy balance, and equilibrium reactors. So we are going to look at them first, the reactors that do not require kinetics. Then later we'll delve into the ones that require the reaction kinetics. So the first reactor we are going to handle is R stoic. We've already seen that in our introductory session. And as the name implies, it's a stoichiometric reactor and relies on the stoichiometry of the reaction being simulated or run. So you specify the stoichiometry of the reaction and it asks for either the fractional conversion or the molar extent of the reaction. So it's a mass and energy balance reactor, and for its energy balance calculations, it requires a specification of the conditions, the operating conditions, whether the reactor is being operated adiabatically, isothermally, or not. And based on this, it's able to perform the required calculations for the process. So we're going to attempt to solve this example using the stoichiometric reactor, our stoic. And we are going to vary the conditions and see what effects it has on the process. So these are parameters. They have sweet natural gas in this proportions is bent in the combustion chamber for a gas turbine with excess air. We have to use our stoic to simulate the process. So here we have the components, the natural gas component, components of air, and some of the expected products from the reactions. Since these are combustion reactions, we expect water and carbon dioxide. And since we are burning in excess air, we expect complete combustion, meaning we only expect these two products, no carbon monoxide in assimilation. So we can head to the property method and specify then Robinson and then head to the simulation environment. So we first go to the model palette where the reactors are. Just like the first reactor, select it. That's our reactor. And then we also have to mix our feed. So we can put that before and then connect the relevant material streams. It's a mixer, 2 feed, 1 output to the reactor, and then a single product stream. Once we are done with that, we come back to our problem, and based on the balanced stoichiometric reactions and molar basis for our feed, we're able to calculate the theoretical amount of oxygen required to completely burn our natural gas. And if you see, even for reaction 1, for instance, for every mole of methane burned, we need 2 moles of oxygen, right, to burn in. And since methane was 90% of our feed stream, the molar flow rate of methane here is 90 moles, and multiplying that by 2, we get the amount of oxygen needed for reaction 1. The same can be done for 2 and 3, and then we determine the theoretical amount of oxygen required for the reaction. And to determine the actual amount of oxygen or the excess oxygen, we multiply our theoretical value by the excess fraction instead of 200%. And that helps us determine the actual amount of oxygen. Then based on the proportions, we determine the flow rate of air that will give us this required amount of oxygen. So based on this, we go back to our simulation and specify the material streams, the operating conditions for the reactions, the pressure, and the flow rate of air. So calculated 20. Sorry. Here the units do not matter. We just need similar proportions and the right similar units. So we're keeping it as kilomoles per hour here, since we just assume the basis. That should be it for the airstream. Sorry, that was a mistake. Should be air. So oxygen to and our natural gas right. We go to our block, and we were required to operate it vertically, and means the reactor or the reaction system is not exchanging any heat with the surroundings. So we go to heat duty instead of temperature, and then we specify a duty of 0. And the pressure should still be the reactant pressure. The next thing will be to input our reactions. Come to the reactions tab, a new reaction. Select our component for reaction 1. This is a reactant. In the fractional conversion here, it's complete combustion, burning everything. And we can add another reaction, reaction 2. So the same thing can be done for do the same thing for all of them. So then we should have this for the third reaction. Should also be as such. And that should give us the liberty to run our simulation. Do that quickly. Anyway, we check results are ready. So we go to the block results first, and you see the outlet temperature of the reactor is 1,256 degrees Celsius, thereabouts. And, that is as a result of the amount of heat generated due to the exothermic nature of the reaction. Also, we can go to our streams, look at the stream results. To our molar flows, and you can see that all of these have been completely used up, minus the oxygen, and we have products. Our results are good. If we go back to the problem, we were to run the reactor at a specified temperature. Temperature of the exiting gas should not exceed 1,100, and to do that, there has to be some heat exchange for that to be possible. That's to be cool. So we do that in SP by specifying a temperature. Temperature that the reactor should stay at. If we do that and run the simulation, oh, go back to the reactor. I think I may have specified a duty for pressure and temperature. Reset the simulation. When we go to our results, we get a duty. So put this in kilowatts, and the reactor is able to give us the duty, right, the amount of heat we have to remove from the reacting system in order to maintain the temperature at 1,100 degrees Celsius. So that is it for the stoichiometric reactor, R stoich. So let's talk about the equilibrium reactors, and we are going to look at R, Gibbs, and in Aspen Plus, there are two of these. For the non-kinetic reactors, two of them that are equilibrium based. The R Gibbs reactor and R R equilibrium. It's a reverse equilibrium reactor. So the R Gibbs reactor works based on as the name implies, Gibbs energy for a process to a reaction. And the condition for a reaction to be feasible is based on a negative change in Gibbs energy. So based on that principle, if there's a set of possible reactions of components, R Gibbs determines the product combination of products that leads to the lowest or most negative Gibbs energy. So that's the assumption the reactor operates. It assumes that the system that will result in the lowest Gibbs energy is the most likely to occur, and as a result, those determine the product composition. So that's how this reactor works, and it's a very useful reactor for a lot of problems or even non-conventional problems, for things like combustion, gasification. It's able to handle solids as well. So it's very useful for a reaction system where we might not know the specific reactions that might occur in or the outlet composition, the respective compositions, but we have an idea of what the product should be or what things we might expect in our system. Right? This reactor is very useful for that. So there are a lot of configurations under which it can be run. And if you look in the material, it's been used for solve a problem. So since it's an equilibrium reactor, it can also handle stoichiometric reactions. But then what it calculates is the composition at equilibrium. It's able to give you the equilibrium composition for the reaction system at the end of the reaction. So if you look in the material, you'd see that problem and how it was solved. So we'll quickly move to R equilibrium, which is what we'll be treating or handling here in this lesson. We will do more on R dips, hopefully in a later time, at a later time or in the future, right? So the equilibrium reactor, as the name implies, is for the simulation of equilibrium reactions. And in this case, you need to know the reaction stoichiometry. It requires a balanced reaction, right? And it has some few restrictions on what the product should be. It should be a liquid and a vapor product, and it's able to determine the equilibrium constant and position for you as well. We are going to demonstrate that using the reaction we saw previously. So go ahead and add the components of this reaction to your simulation. We're still maintaining the Penn-Robinson equation of state. And here we pick the equilibrium reactor. After we have done that, we can label the streams nicely and go on to the specification. Conditions are at 450 Kelvin and 4 bars of pressure. Then say for a 4 kilomole per hour case, we feed stoichiometrically. So the nitrogen to hydrogen is 1:3. That should be it for our feed. We'll do the same for our reactor. Then to add our reaction, so we go to the tab in similar fashion. And once we are done with that, then we should be able to run our reaction simulation. Sorry. So when we check out the results, see the outlet temperature, pressure. It's able to calculate the duty for us as well. And importantly, it's able to give us the equilibrium constant conditions at equilibrium. So this summarizes our work on the first set of reactors. We will be looking at R yield, the yield reactor as well, but more on it in detail in the future. And it works by calculating the composition of the product, outlet composition based on the yields supply. It's the user supplied yields. And it's good for certain kind of reactions like bioreactions and some of these solid phase reactions as well, where we might not know the reaction pathway or have a good idea of what a stoichiometry might be. But if experimental data has been carried out or gathered, experiments have been carried out and the data has been gathered, and we have an idea of what the yields are, then this is a very good reactor for simulating those kind of problems. So just by specifying the yield for the products, we are able to determine the outlet composition. Right. And so if you look at this problem where you have a feed and we have an idea of what the product should contain in the yields of the products. And this is given to the yield reactor, which can be located down here. The yield reactor. And when you, in similar fashion, you specify conditions of streams, and then it asks for the component yields. Right? So there are lots of options on how to supply the yields to the reactor. But they ask for the component yields, and you're able to select components. Say for a case where I connected some streams and specified, yes, provided some specification for what it should be. And then when I come back here, I'm able to choose the component, maybe my product, the basis, and then the yield. And after supplying this, it calculates the other composition from right. So the next time we meet, we'll be talking about the kinetic reactors, the reactors that require the reaction kinetics. Right? And they are, we'll look at some of them, how to specify the reactions, the kind of parameters you might need, and how to handle the parameter specification in Aspen Plus. Thank you.